Are you coming today especially for this lab, or you had another thing? So I'm coming especially for my lab.
Yes.
It's okay. I will revise again Dijkstra fast because it wasn't fully recorded in the previous lab. Okay? So I will revisit the Dijkstra algorithm fast, then we can proceed with the second problem. Do you remember the first problem?
Yes.
Was it clear? It was also recorded. If you remember, it was like having some super notes you can, in order to calculate only the Dijkstra once, and after having each distance from each junction to the nearest motion sensor, we can then do what? We can then determine whether there is a path from the entrance junction to the matching junction. You remember? But which value do we want? We need the largest K value in order to minimize the probability of being detected. That's right. So in order to do this, we had three approaches. First, moving from 1, 2, 3 till K star no plus 1. Because if K plus star plus 1 fails, then K star is the largest possible value that ensures that there is a path from star to target while maximizing the K, or in other words, minimizing the probability of being captured. Or code. Okay? Did you got it? Okay, at the end we had another approach. We said that we can binary search, we need some intervals. So we said we can binary search from 1 to the largest or the maximum shortest path, if you remember. Because if the maximum shortest path is our key, we are sure that every junction will be eliminated. Because a vertex will have a smaller distance than this maximum one. That's right? So we are sure that all the rest are eliminated. That's right? So in order to solve this, we said that it's also unbounded. Because here I am looping till, or I'm making binary search till something called Z bar, which is the maximum distance out of all distances. That's right? But this is unbounded with respect to n. That's right? So we said the last approach was to binary search on the array of distances itself. Because if 8,000 fail, sorry, if I have some array, the middle is 90,000. If 90,000 fails, then I will go left or right? Left. Because it fails, there is no path. There is no reachability from S to T for 90,000. So I will go check 8,000. If 8,000 works, or not 8,000, sorry. If I move to 1,000. It works, so I will go right. 8,000 also works. The best case, when I found the middle works, and the one after the middle doesn't work. I'm sure that this will work. Do I need to check for every other number in the interval?
No.
If 8,000 works, it will eliminate any junction with 8,000 or less. Okay, if I told you 90,000 didn't work, 9,000 minus 1 will also eliminate those 4. So no need to check from 8,000 to 90,000 because anything between them will eliminate the same that will 8,000 eliminate. You got it? So in order to this, we had 3 n log n, 1 n log n for the Dijkstra from the super node, 1 n log n for the sorting, and the remaining n log n was log n for binary search, and each time I checked the reachability using PFS, which was n. Did you remember the problem? Is it easy? We'll discuss it in 5 minutes. It's not hard in the final. That's right.
Well, it's easy in the first place.
Yeah. Okay. Let's revisit Dijkstra fast. Dijkstra is called a single source shortest path algorithm. What's meant by single source? It means that I need only to begin with a single source, and from the single source to get the minimum distance to all the remaining vertices. So starting from here, from this A, this is a single source starting point, that's right. I will start from A and get the minimum distance for all the other vertices within the graph. How can I do this? First, I will pick the minimum. The distance for the starting point is 0. Any other distance is infinity. What's the benefit of making other distances with infinity? We have two benefits. First, we need to minimize each time. So we need to begin with a very large number like infinity. The second benefit is that we need to know if at the end we have some vertices with infinity, it means that they are unreachable. Because if they was reachable, the value will not be infinity. It will be something smaller, that's right? So to be minimized when going through the graph or when traversing the graph. That's right. Okay, beginning from A. What is my neighbors? B and C. That's right. Okay, B and C both have distance infinity, and I can go with this distance. I can go with 3 only. 0 plus 3 or infinity? 3. So I will update this C to have a value of 3, and the parent will be A. What about B? I will update it with 10, and the parent will be also A. That's right. But first I will initialize the A with distance 0, and there is no parent because it's the starting point. So it has no parent, which is called a null parent or something like that. Okay, so the A will update 2 neighbors, which are B and C. Both will have the same parent, which is A. That's right. Is there any problem till now? Is it clear? Okay. Second, I will pick the minimum out of the remaining. Which vertex I have already finished? A. Because I have explored already all of its neighbors, so it's considered visit. Meaning that it's finished because I have already updated its neighbors. So I will put it in a visited list. Now I have some remaining. All of them except A is remaining. Which one is the minimum out of all of them? C. Okay, what we are doing here? Each time we are picking minimum out of the feasible ones, that's right? Which is the approach that this fall into? By greedy. Right? The greedy algorithm. So the Dijkstra is a greedy algorithm. Why greedy? Because each time I follow the same procedure. My problem is selecting the minimum and updating the neighbor. What is the problem? I will just say but with n minus or v minus. So it's divide and conquer but with only one subproblem. So here's the optimal substructure holds. But each time I do the same thing but with a smaller subproblem. First I have n, pick the minimum, change the neighbor, n minus 1. Pick the minimum, change the neighbor, n minus 2. Until you reach the n. That's right? So we only have each time one subproblem, which is considered the greedy approach. Is there any problem till now? Okay. Whose term now? C. Who are the neighbors of C? B and E. Okay. E has and D has. E is infinity. 3 plus 2 is infinity? 5. So I will update it with 5 and I will make the parent C. What about D? 3 and 8 is 11. I will update and make the parent also C and the same goes for B. 3 plus 4 is 7. I will update the parent. Yeah, but 3 plus 4 is 7. 7 is smaller or 10? It means that I have reached vertex B with a best distance so far. Because it's minimum than the previous stored one. That's right? So I will update those 3, including the B, and all of them will have the C as a parent. All of them have the C as a parent, and now we have the best distance till now. Okay, what is the minimum? Now we have 2 visited, so I will see the minimum out of the remaining, which are D, E, and B. Who are the minimum? E. Okay, E only goes to D. 5 plus 9 or 11, which is already stored 11. So I will do nothing. That's right. I will not change the parent because I have already recorded it with a smaller distance. Okay. Okay, now we can pick the minimum from B and D. The minimum is B. Okay. Who are the neighbors of B? We have D and C. C has a value of 3. 7 plus 1 is 8. So this will not work. I will not update anything. What about D? 7 plus 2 is 9. 9 is smaller than 11. So now I will update its parent. Its parent now is B instead of C. And it will have a new value which is C. 9 instead of 11 because it's the minimum until now. That's right? Now all of the vertices are already visited. Means I have updated the neighbors of all vertices. So now I am sure that I have got the minimum from the starting point to all other vertices. So now I have finished the algorithm. Is there anything hard? You have any question for this? For sure? Okay. Let's look at the pseudocode first. We have already discussed this in the previous lab, but I'm revisiting it quickly. First, I need to insert the starting point or the single source that I'm starting from with 0. That's right? all the other vertices will have a distance of infinity. That's right. Okay, so I will initialize all the other vertices with infinity. I will insert all of them to the Q. So now I have how many vertices in the Q? The starting point and all of the others. That's right. After this, I have initialized an empty visited list, and I'm looping until the Q is empty. As well as the Q is not empty, loop, and get the which value from the Q? The minimum, right? So I will extract each time the minimum from the Q. Okay, and put it into the listed list, which is T. Okay, then I will do what? I will check the neighbors for you and see whether the best value for me, with the H going for the neighbor, is better, or the previous still going for the neighbor. If it's better or smaller, I will update it. Otherwise, I will leave it. That's right. So I will check when I'm at U. I will check for all the neighbors for U, and check the best distance for U. Plus the H weight is better, or the one stored for V. If it's better, I will update it and update the parent for it. Otherwise, I will do nothing. That's right. So if the distance with the H weight is smaller than the one I'm going to, which is the destination or not the destination, the vertex that I'm going from U to V, if the distance for U plus the weight of the H, it is smaller than the one stored already for V, for my neighbor, I will update the distance and update the parent. That's right? At the end, I will return both the distance and the parent. What is the benefit of returning the parent? The distance already states for me the shortest path for each vertex starting from the starting point. That's right. Okay, what's the benefit of having this parent? That he only tells me the best value for the distance, the smallest value, the shortest path. It doesn't tell me how to get this path. In order to get this path, I need to traverse through the parent. I should like begin from the destination, see its parent, and see its parent until I reach the starting point, and then I can reverse the array to get the correct order for the path. Did you got it? Do you have any question till now? Are you sure? Okay. Let's first go with the analysis for this part. Okay. How many inserts do I do in this code? How many inserts?
V first.
First, I insert the first starting point, which is one time, one insertion. And then I insert all of the remaining to the Q. So insert is called how many times? V times, with each vertex, that's right? So insert is called V times. Okay, why did he didn't specify the complexity for the insert? Because it's different from one data structure to another. The complexity for the insertion and update and delete differs depending on the data structure used. So you use Fibonacci D, it's different from priority Q, different from normal array, and so on. Okay, so I don't specify here the insert complexity. I only know that the insert complexity is repeated how many times? 3 times. Okay. What about the extract minimum? How many times will I call the extract minimum? I'm extracting the minimum each time from the remaining vertices until the Q is empty. How many vertices do I have? 3 vertices. Each time I will extract the minimum. This will be visited, and I will extract the minimum from the remaining the next time, and so on until the Q is empty. So I will do this process how many times? V times. So I will extract the minimum how many times? V times. Is there any problem till now? Okay, what about the update? How much time will I update? If my current plus the weight of the edge is smaller than the destination or the neighbor, that's right. But what's the maximum time I can update?
Number of neighbors.
Number of neighbors, that's right. Those two loops, the first loop on the Q and the second loop on the neighbors for each vertex. So this extracts the current vertex and this loops over the neighbor for this extracted vertex, that's right. So this loop plus this loop will be exactly E, that's right. Because with each neighbor I'm looping over, so with each vertex I'm looping over its neighbors. And the second vertex I'm looping over its neighbors. So at the end, when both loops terminate, I will have already looped on all of the edges. That's right. In order to reach the neighbors, I need to go through the edges. I do this each time with each vertex, so I will loop over the whole edge in the graph. Okay, but will I enter this condition each time?
No.
No. So it's upper E. I will update upper E. Okay? You understand why it's upper? Because it's not, I cannot guarantee that each time he will enter this condition. Maybe he enters one time and doesn't enter the other time. That's right? Okay, so the overall complexity is what? Is exactly V times by the complexity of entry plus V by the extract complexity plus E by the update. And those will be different depending on the data structure used. So we can have 3 data structures which are commonly used for this. The most common one is the priority queue, but it depends whether I should do which one. There is no like specific one that I should always use for the Dijkstra. It depends based on the type of graph, based on the properties of the graph. Okay, so first let's go with the normal array. In order to enter in an array, how is the complexity of this? What's the complexity? In order to enter it in a normal array, what's the complexity? This one, I will make A of 3 equals something, A of something equals something, that's right? It's order 1. You have a question? Did you get it? What about the update? How to update in an array? A of something equals something also. Exactly like the insertion, that's right? Or it's order 1. What about the extract minimum?
3 times. Because without it,
I need to traverse or search all over the array until I reach the minimum. That's right? I need to exactly move V, which is the number of vertices. That's right? So here it will be V by 1 which is V, E by 1 which is E, V by V which is here it's an upper E. Why upper E? Because as we stated, I cannot update each time. It's an upper bound. Because sometimes I can update and sometimes based on the value of the neighbor distance. Okay, yeah, exactly. So here it's you have any question till now? What about the second one? The priority queue inserts, deletes, and updates, and like extract the minimum. All of these operations are log V. Log V. Yeah, because it uses something called maximum heap or minimum heap. Like if we can imagine the minimum heap, something like it's something in it's some data structure that specifies at the root it must be the minimum value. So the minimum value is at the root. Okay. The two child will be greater than this root, and each one is considered a new root, and the children of it must be larger. If we are minimum heap, this is the minimum, those are larger. This is the minimum, and those are larger. Each root is considered the minimum with respect to its leaves. Okay, you got it? What about maximum heap? It's obvious. Here is the maximum, and those are smaller. And this root is the maximum, and those are and so on. Okay. In order to get a minimum from something like this, I need to traverse, no, not minimum, so in order to insert or update, I need to traverse the number of levels, which is log V. That's right, so it's log V. Okay. What about the extract minimum? Also it's log V. But some people got confused regarding the extract minimum. I have already told you the minimum is stored in the root.
But you have to find a new.
That's right. But in order to find the minimum, it's O1. But I need to get a new minimum to be the root. So in order to make this rearrangement, it will take log V. So the next time I can get the right minimum. Okay? So in order to ensure that the minimum each time is stored at the root, I need to make a rearrangement which will take log V. The extraction itself is order 1, but the rearrangement is log V. Did you got it? The first chip is similar to priority queue somehow, but the insert and the update is order 1. But the extract minimum is the same. Did you got it? You have any question? Which one is the better? Or it depends? Depends on what? What's meant by density graph? Means that mostly every vertex has a connection to any other vertex. So if we have some vertex, we can say that it has at most V minus 1 connections. The same goes with every vertex. So we can have all V square vertices. Yeah, V square, like it's almost V square vertices. Sorry, V square connections or edges, that's right. So here it will be V square log V. And here it will be V log V plus V square. Which one is the smallest? But this one will be like V square and this V log V, so it will be like this one. But the Fibonacci will take extra overhead, unlike normal array. So when we have dense graphs, we should only go with this normal array. It will be much fast, much easier to implement. Everything will be better. But those are suitable with sparse graph, while this is dense graph. Did you got it? What's the benefit for Dijkstra? What's the benefit using Dijkstra? Getting the shortest path, right? Yeah, but what is the disadvantage? What's the disadvantage? Disadvantage doesn't work with negative edges. So the advantages of Dijkstra, it finds the shortest path. You can only find it in a very small complex, which is E log B. E log B is considered very small, because it's like somehow linear, right? But it doesn't work correct like all the time with negative edges. Okay, did you got it? Let's proceed with the problem. You have a question till now? Okay, but I will ask you some question. What is better for getting the shortest path? Using BS or Dijkstra? We have taken in the lab, like before that, for this week, BS algorithms, right? We took like many problems with BS variations. We was using BS for getting the shortest path sometimes. Should I consider using BS or Dijkstra? If the graph is weighted, if it's unweighted, I will go sure with for sure BS. But if the graph is weighted, it depends. It depends on the weight. Is the value of the weight constant? If it's constant, I can go with BS. If it's something like with respect to the number of vertices, like 10V, 20V. If I told you that the total edges in the graph is 10V, 20V, somehow related to the original complexity. So it will also be B plus E. So BS will be better. But if the weight value is unbounded, unbounded means it isn't related to some constant or to some V. So it will be maybe like B much more than V plus E, so it cannot be changed to unweighted. So here will be, the Dijkstra will be better. So most of the problems that have weights, I can go with the Dijkstra. But if the weight is almost constant or with respect to the input, I can go with BS. Did you got it? You have any questions till now, right? For sure? Okay. Let's see the second problem. We have already revised the first problem. Do you have any question for it? Okay, I will discuss the second problem. Okay, I will write the second problem and you can focus on me because it's very important. What's the complexity of the Dijkstra? It's for probability Q, it's E log V. That's right. Let's write the probabilities for the graph. We can have the graph weighted or unweighted. We can have it. First we can have it directed or undirected. We can have it also weighted or weighted. Yeah. Sorry. We can have it connected or this connected. You can also have it sparse or okay. What does the problem states? The problem is called crater collection. Do you know what is crater? Crater is like monasteries. Monasteries. Okay, so he tells you here, Ashley wants to go from a city called Trundle town to Blue Okay, there is a girl called Ashley that should go from a Trundle town, a city called the Trundle town, which is a source, to the target, which is a city called the Blue Bluff. Okay? He tells you the map that Ashley will go through has n clearings. Clearing is like places, has n places or n clearings, okay? Connected with two-way trials. Okay. He tells you that the map that Ashley will go through in order to visit or to reach the target has n places or n clearings connected with two-way trials. What is trials? It's a busway or it's a road. Trials like a road or busway that go from one place to another place, or from one clearing to another clearing. Okay. Okay. First, is it directed or undirected? Two ways mean I can go from A to B or from B to A. So it's an undirected graph. So we can state that it's an undirected. Is there any problem till now? Okay. So he tells you also each clearing connects at most 5 trials. Okay, he tells you each clearing, each place connects at most how many trials? 5. So is it sparse or dense? Tells you each clearing connects at most 5. So he didn't tell you n trials, only 5. We assume that n is a very large number because it's unknown, it's a variable, it's an input from the user, that's right? So I cannot assume that it's a small number like 5 or something like that. We assume that it's a large number. That's right? So here we will consider it as sparse. Yeah. Okay. Then it tells you each trial connects to clearings with lens, healthy, and okay, it tells you each trial or each road connects to clearings. Who are the clearings and who are the trials? The clearing is considered what? Vertices, right? While trials are the edges that allows me to go from one vertex to another one. That's right? Okay. He tells you with length LT and crater CT. This means it's weighted or unweighted. Each trial connects two clearings with length LT and the craters CT. So the length of the road is its weight. So it's weighted, that's right? Because different roads have different lenses. So it's weighted. Okay, do you have any questions now? Is my handwriting clear or not? Is it clear? Okay, he tells you here that this girl Ashley, she needs to collect every crater or every monastery she encounters in her way or by throwing an empty bucket sphere at it, or she will be sad. Tells you during Ashley's adventure, when she is walking from one city to another, she's moving through some pathways or some trials. That's right? And she's moving from one clearing to another clearing until it reaches its destination. That's right? It tells you when she is moving through a trial, focus. She tells you that when she is moving through a trial, she may encounter some critters. Okay, those critters should be collected, because if she doesn't collect those critters, she will be sad. Okay? Okay, so he tells you that she has some empty bucket spheres. She has some empty bucket spheres. When she threw this sphere on the critter, she collected. Okay? So if at some point she finds a monster or critter and she don't have a bucket sphere, she will be sad because she can't collect it. Okay? So we don't need her to be sad. Okay? It tells you also there are stores. There are stores at some places or clearings where Ashley can buy empty bucket spheres up to K. Good. Right. He tells you there are some stores at some clearings. Those stores, Ashley can go through them in order to buy empty bucket spheres. Okay, she only can buy up to K because of her bag capacity. The bag only can hold K spheres. She began also with K spheres. She began with K spheres. She initially had K spheres, and at any store she can only fill her bag up to K because of her capacity. Okay. What does he find, or what does he want at the end? He asks you to find the shortest path in order NK log N K without being sad or return that sadness is unavoidable. Okay. Do you understand what is the requirement here? What's the requirement here? He tells you at the end, we need to find the shortest path, but ensuring that Ashley will not be sad, or returning that the sadness is unavoidable, meaning that any path I will go through will make me sad. Happy? Not happy? No sad? No happiness. Okay, how can I ensure that? The problem?
So if she's sad, then game over.
Yeah, if she's sad, then game over. So if we have if we can reach the target beginning from the starting point through 100 pathway, if 50 of them will make her sad, I will only get the shortest path from the remaining 50. Okay? So if I have 50 pathways, 30 of them will make her sad, so I need to get the shortest path out of the remaining 20. So I need the shortest path, but without making her sad. Meaning I only need first to filter out the paths that will make her happy, but will make her not sad, and take from them the shortest path. How to make this? Should I help her in collecting the critter? What should I do?
Yes, no problem.
Is this problem hard? Actually, needs to be happy and you will be sad in that.
Can you illustrate?
Yeah, I will give you an example, like a drawing example so you can imagine it more, but until now you are understanding the problem itself?
Yeah, you understand the problem.
Yeah. But do you understand how to solve it? No. Very good. Okay, I will give you an example. Here, some like visual example. Here's a case for. What is this key? This key is the capacity of the bag. So it's the number of pocket spheres that actually can maximum have. That's right? Okay, so I will tell you here k equals to 4, for example. K equals to 4. And here I will have S. C. E. Okay, so here are some clearings, each connected with some busways, and I can have maximum 5 busways from each clearing, right? Okay, let's take some like quantitative example here. Here I will write 2 numbers on the edge, like considering both the length and the number of critters, okay? So the first number will denote the length of the edge or the busway, and the second will denote the number of critters that I will counter when going through this busway, okay? Malone, did you sleep? I didn't finish yet. Try to focus. Okay? So here I will have 15 and 3. 15 means that the length of the edge or the busway is 15, while 3 means that I will encounter 3 critters when going through this busway, okay? Okay, what about here? It's 8 and 1. Here it's 5 and 4. Here it's 6 and 1. Here it's 6 and 1 also. Here it's 4 and 1. We also stated that this clearing has a store, meaning I can fill my bag, however, or despite how many spheres do I currently have. It doesn't matter because I can fill my bag at any store, but only up to k because of my bag capacity. That's right? Okay, how to solve it? What if we solve it using Dijkstra? What does Dijkstra do? I'm the shortest path beginning from some starting point. I will begin from S until I reach the target, which is T. Because he told you she's going from trundle down, which is the starting point, to the target, which is blue blood. Okay, so starting from here, go to the target. How many busways can I go through? I can go through this first one. 6 plus 4 is 10. 10 plus 6 is 16. Okay, this is the first busway. Second busway, 5 plus 6 is 11. The third one is 15 plus 8, 23 plus 6 is 29. 29 or 11 or 16? 11 is the shortest one. So the Dijkstra will stick with this one. Why? Because he only cares about the shortest bus. The purpose of the algorithm is getting the shortest bus, that's right. Okay, so here, what will happen? Going from S to B, I will encounter how many critters? 4. So I will be left with 0 spheres. When going to the target, I need 1. I will encounter also 1 critter, and there is no store. So what will happen? She will be sad because she will encounter a critter and she cannot collect it because she has no spheres now. Okay, so the Dijkstra field here. What should we do? What should be the answer? I have 3 busways. How many of them are valid? Is this valid? 4 minus 1 is 3. 3 minus 1 is 2. 2 minus 1 is 1. So going through this busway, I will be left with 1 sphere. It means that I have already collected all the critters that I have encountered. That's right? Okay, what about this busway? 3 from 4 is 1. But I will have a store, so I can collect 4 spheres, so I can get 4 spheres again. 4 minus 1 is 3. 3 minus 1 is 2. So both busways will make her happy. But which one is the shortest bus? 29 or 16? So I should not return the shortest bus. I should return the shortest bus when being not sad. So here is the trick. How can I do this? The Dijkstra, as we stated, it will not get me the correct answer. Can I make an no? Because it's all make the same like the Dijkstra but with unweighted graphs. It's weighted, so I cannot do this. What? Yeah, the Dijkstra is greedy. But greedy is a concept, not a solution method. The problem here is doing the Dijkstra will get me the shortest path and will not consider the principles. I will only consider the length, so there's something that I specify that I need to minimize. I need to minimize the length, but holding that the critics will not be collected. The speed will not be valid. That's right. So how to ensure this? Is there a workaround to do this? Think about it. I will give you points if you can't answer. That I can say. I need to find the shortest bus, but without being sad. She not me. So how can she do this? The problem here is that the speed may vanish, like in this pathway. 4 minus 4 is 0. 0 minus 1 is minus. So it means that I have encountered a critter and I cannot collect it because I don't have enough spheres. That's right. So I will be sad, but the Dijkstra will minimize this pathway because this is the shortest one. 5 plus 6 is 11, which is shorter than any other pathway. So I don't need this. I need first to see the passes that are valid, which will make her not sad, and then get from them the shortest pass, not from all the passes. How can I do this? No.
So you might have to find path that contains the greater path.
Yeah, but it will give you the minimum. It will let you go to the target with the minimum number or with maximum number of spheres.
Yeah.
But you don't mean this. For example, here you will go with how many spheres? Here 1, 1, 1, which is you will be left with 1 sphere. But here it's 4 because I will go to the store. 4 minus 1 is 3. 3 minus 1 is 2. So which one is the minimum? Which one is the maximum? Sorry? 2. The answer is this one.
Maximize your space and minimize the distance.
How can I do both? I cannot. I should describe this or this. You need to understand what is the issue. What is the issue? The issue is about that I go to some states which are negative, having negative number of spheres, meaning that I encounter some critters and I cannot collect them. So how to resolve this? Tell me.
I'm not sure what's this.
I think bonus to you are trying to figure it out.
Divide for by each increaser. Each increaser divide against the ratio.
Okay, again, I can see you.
This for example.
Yeah. Think again.
You take the ratio of the increaser.
What?
Take the ratio of the increaser to the number of increasers that I have.
Yeah, what will we do? We take number of critters and then
Just and divide it by each increaser. Based on that, we'll discuss.
not going
The
to
goal is to maximize space.
I need to minimize the number of critters that I will encounter or maximize the speed. It doesn't matter. But this is not my goal. My goal is not to be sad. Regardless the number of critters that I will collect. No. The goal is to not be sad regardless of how many spheres will remain with me. It doesn't matter. What does matter? That I will not be sad. After not being sad, I will should see the minimum busway. So what matters? The minimum busway, but after not being sad. Being sad, not being sad means that I will collect every critter. It doesn't matter, I will be left with 2 spheres, 5 spheres, k spheres, doesn't matter. What matters is that I will not be sad. Meaning collecting every critter that I should encounter. Okay, let me give you a hint. Look at the complexity. What is the number of edges here? N. What is the number of vertices here? N also. So it's N log N. If I make one Dijkstra, it's N log N. He tells you I need it in N. K log N K. Where K is the number of spheres. What should I do? Can I play with the graph itself? How can I like alternate the graph itself, the graph structure, in order to resolve this problem? Do you have any suggestions, or I should go on? Any opinions? You got 11 in the midterm, I think you can have it.
Just want to try to share.
Or you are afraid from your friend noise.
I think you can perform the first time. Then if you are not able to get both repeaters, you can perform it again to get the next one.
But how can you from the Dijkstra first? He will give you this. You know that you have been sad going through this busway. So what you should do when you eliminate the edges? If you eliminate the edges, maybe some edges will be like common in other busways. So you cannot eliminate the edges. But if you will repeat the algorithm again, it will give you the same answer again and again.
So like take Dijkstra for the distance, then for the distance first, then the distance.
No. So the credit is first. You guarantee that you will not be sad.
But you don't know the shortest distance. Then you take Dijkstra again for the distance. Do you understand? So two Dijkstra.
Yeah, I understand, but how the first Dijkstra, how would it affect the second Dijkstra? The first Dijkstra will do what? How to describe that this bus is not valid? Will you remove the edges for this bus? If you remove the edges, maybe this edge is useful for other busways. You understand me? Like something like this. If I have A, B, T, this is the target, okay? And I have here C and T. What if this busway didn't reach me the answer? I was standing this busway, so I can remove this edge and this edge. So now I cannot reach D, but this bus can reach me. So how will you know from the first Dijkstra the second one needs to avoid this busway? You can't specify this. This is the problem. You are thinking correctly, but this is the problem. You cannot specify this. Okay, I will tell you, because we don't have any time for this.
One try.
Yeah, tell me.
What if you add loops?
What?
What if you add loop?
What if I had what?
Loop.
Loop over what?
Changes.
Let me proceed with the answer, and I will try to give you some hints. Okay. It tells you here what are the valid states. Going to any clearing will be valid if I am not sad, right? Meaning that I will have positive or negative spheres. Positive spheres. If I have negative spheres means, or not negative spheres, if I have no spheres or the spheres vanish and I encounter a pressure, I will be sad. So I need to check over each state. I will need only to consider that positive states from 0 to k. What's meant by this? Going from S to C will be valid when I'm sure that going from S to C will make me not sad. If I want to see, this is how many spheres? 0, 1, 2, up to k. If I want to see with k spheres, it's okay. 1 sphere is okay, 0 sphere is okay. But if I want with negative, it will not be okay, that's right. A 0. 4 minus 4 is 0. 0 minus 1 is negative. So here I cannot go to this state. So in order to ensure that I cannot go to a negative state, I will only make a new graph with every possible state for every vertex. What's meant by this? Focus with me. I will do what? Here, k is equal to 4, that's right? Okay. I will begin from S and the k. Okay. I will have here, I can go to C with how many valid states? How many valid states? I can go to C. Work up. How many states how many valid states can I go to C? I can go to C with 1 sphere left, with 0 sphere left, or with k sphere. All of them are correct. That's right. So I can go to this C. I can here, no, that's not the first. Write the states. I can go with C and 0, C and 1, C and 2, C and 3 up to K, which is here 4. What about the A? That's the same.
Yeah.
I cannot exceed K. and I cannot have a negative state. Negative state means that I have encountered a critter and I cannot collect it. So here it can be A with 0, A with 1, A with 2, A with 3, A with 4. Did you get it? What about B? Can I also B with 0, B with 1, B with 2, B with 3, and B with 4. What about T? T with 0, and so on. Okay, what will I do now? I will only connect edges for only the valid states. What do I mean by this? Okay, first from S to C, how many critters will I encounter? 3. So to require how many spheres? 3. So which state will I go to? From S, I will go to clearing C. With how many spheres? With how many spheres? I had 4. I took in the pathway 3. I counted 3. So I will reach C with how many? 1 left. So here the state is going to C with only 1 sphere. That's right? Okay. The cost here will be 15 and I will count 3 correctly. Right? Is there any problem? What? Again? Okay, again. Here from S and K. The K is 4. Okay, so when I go to C, how many critters will I encounter in the trial? 3 critters. That's right. Okay, so when I have 4 spheres, I need 3 spheres for those 3 critters. So I will be left with only 1 sphere. So this is a valid state. Why? Because it's not negative. It means that I can collect any critter that I encounter. Because the sphere is more than the critters till now. Okay, here, luckily, I have here a store. So I can refill again all of the spheres to K. That's right? Okay. What about here? 6 and 1. Which state will I go through? I will go to clearing 3 with how many spheres? 3. Because 1 will go for this critter and I will be left with 3 now. That's right? So I will go to this having, I will go to A with the state of having 3 critters. Sorry, 3 spheres. We have already collected a critter with 1 sphere. Okay. What about C? How can I go to B?
B3.
8 and 1. That's right? But here luckily I have a store. So should I continue with 1 or with K? Because in the store, the best solution is to fill all of the bag. That's right? So I will go from 1 up to 0, from 1 to 3. Because I've already filled the 4. That's right? Which costs 8 and 1. 1 critter. 1 sphere. 1 critter. Is there any problem till now? What about from A to B? I will have 1. And then now I have 3 and there is no store. So I will have only left with 2. So I will go to B while having only 2 spheres. And here it's 4 and 4. That's right? What about the S? Going from S to B requires collecting 4 critters. So it requires 4 spheres. So I will go to which state?
B0.
B and 0. And here it's 5 and 4. Okay, very good. Okay, what is left? Now, going from B to the target. I will encounter how many critters in the trial? Only 1. Okay, so this one, do you remember this one? I told you this one is not valid. It's not valid. Why? Because it will not avoid sadness. She will be sad, that's right? But here when I make a state with the positive numbers only from 0 to K, here can I connect an age to a valid state? Is there a state for -1?
No.
So there will not be a connection from this B to this T. But for both of those, B and 2 will get to 2 minus 1 is 1, so we get to 3 and 1. The same for 3, we'll get to 2. Both with the same thing. I have only added like some states, key states at each clearing, so I can go to some specific state. but I guarantee that I cannot reach a negative state. Means that these busways all have all I got to all those busways without being sad. Okay, how now to get the minimum? We are now sure that we are not sad. Why? Because all the states are valid. Yeah. But how to get the minimum?
Summing up all the distance.
I have two states. Which one of the minimum? Both of them guarantee that I'm not sad. It doesn't matter how many states do I have. It doesn't matter. What matters is that I have collected every crater that I encountered. That's right. So which one I will take of those? The minimum. As we said here, this is not valid. This is 29. This is 16. Which is better? 16. I will find this 29. This is 16. So the better is the minimum, which is 16. Okay. How to know that sadness is unavoidable? Can you tell me? It's very easy. I can make it a bonus. Sadness unavoidable means that I will be sad in any way. How to know it from this graph? What?
If we can finish the T.
How to know it from the distance? Yeah. We have distance for each node. How to know that the sadness is unavoidable? That's the distance for each vertex in the beginning.
Okay, to know like from the part that the sadness is unavoidable, like unavoidable, then maybe when you compare the amount of craters to
Like how to know the sadness is unavoidable? How to know from this graph? Like, how can I know that the sadness is unavoidable?
how to know like sadness is unavoidable.
Yeah. Based on what? What? Yeah, this is the craters, yeah, but how can I know it? Like,
If none of the trails leads to the destination.
yeah, I understand, but like, it depends on two things. Any one of them is correct. If there is no connections to any state, what is the better option is to check for the value, the distance from this. We at first said that we initialize all of them with infinity. So if all of these distances are infinity, so all of these states are unreachable from the start. If all of them are infinity, then the minimum is infinity. When the minimum is infinity, means that all of those states are unreachable. Right? Meaning that all other states will give me to a negative state. That means that I will be sad. So I will return time is unavoidable if I check over all of these states from 0 to k for the target and I found that all of them are infinite. Means that those distances didn't change any time. Meaning that there is no pathway for those, or they are unreachable. Did you get it?
So T0, T3, and T4, they're infinite.
Oh yeah. So I will check from those 5 numbers are all infinite. If all of them are infinite, then the minimum will be infinite, meaning that there is no pathway. That's right. But if only one of them is not infinity, means that this is the shortest path without being sad. If I have many of them, I will take the minimum. Did you get it? So let's say the last thing before we finish. We can have two things. We can have a store and we cannot have a store. The clearing can have two properties. Either being having a store or not having a store, that's right. So here, what if A has a store, and what if A doesn't have a store? What if A doesn't have a store first? Which edge will I do? I can do connection. I can like make an edge or a connection when there is no store. That connection will be valid only and only if when again if A doesn't have a store, I will make an edge of length L from what? From V, some vertex called A and I. That's right. What is VAI? The clearing is A. Okay? Some clearing called A, and the I is the number of spheres that I have. Okay? I will go to what? Another clearing. Let's denote it as B. So V, B. And what? Will I have the same I? Depends on how many critters I will encounter through this trial. So I will have I minus something like C, which is the number of critters. That's right? This H holds correct, or I can draw this H only and only if. When? I can draw this H when?
You can what?
I can draw this H. Here I have drawn the H. Here I can draw the H. Why? Because B is 0, so I is 0. 0 minus 1 is minus. So I cannot draw this H. So I can draw the H only. If the value of I is what?
If the value of I is
Greater than 0.
No, not 0. Yeah, exactly. Greater than C. If I encounter C greater, then I should have only at least C spheres, that's right?
Yeah.
So it only holds for what? For every I belonging from what? From Z to K. Do you understand why? Because if I encounter C greater and I have C minus 1, can I go through this pathway? C minus 1 minus 2 will be minus 1. And there is no field for minus 1. So it means from this that I will only make connections or edges for positive, or for when I guarantee that I will be left with number of the spheres. Right? What about having a store? If I have a store, I will make an edge from what? From VAI also to VB and what?
K.
G.
Does it matter how many spheres do I have? Or I will refill?
Just review.
But I have a store.
Yeah.
So I will go to what? I minus C or something else?
To K.
Yeah, exactly. I will go from I to K minus C. Because it doesn't matter what's the value for the I. It's 2 spheres, 10 spheres. I will refill to the maximum value, which is K. So like here, it didn't matter how many spheres do I have, like 1. I refilled to till 4 and moved from 4 and subtracted 1 also only. So I will subtract K minus C, not I minus C. You got it?
Yeah.
This holds true for which value of I? For each value of I. For every I belongs to what? Doesn't matter what's the value of the I. If it's 0, doesn't matter. If it's 1, doesn't matter. Because I will refill. So it holds correct for any I from 0 up to. But here it must be at least C. Why? Because if I have less than C, so this bus will make me sad. So I cannot make an edge. So when I don't make an edge, I'm sure that I will not reach the target from this busway. If I can't reach the target from any busway, it means that all the target states will be infinity, meaning that I cannot avoid sadness. Did you got it?
Yeah.
For sure? Is there any problem regarding this? Have any question? Okay, we have finished. If you have any question, you can tell me.
You understand us?
You didn't understand this?
Yeah.
Okay, again, let's revisit this again. Going from VAI, meaning when I am at clearing A and have I spheres, I can go to another clearing, let's denote it as B. Okay? Going from A to B, will I maintain the same number of spheres? Depends on how many critters will I encounter. So if I have I spheres, will I maintain the I? Or I will subtract it from some critters? Or subtract it from the critters that I will encounter. So instead of having I as it is, I will have I minus C, because I don't have a store. So if I have 4 spheres and I encounter 3 critters, I will have only 1 sphere, which is I minus C, which is 4 minus 3. That's right? Otherwise, if I have a store, doesn't matter how many spheres do you have. Why? Because you will refill, actually will refill her bag.
Yeah.
So it will have again K. So it doesn't matter I is 0, 1, 2 or K. I will each time go to K from B to K minus C. So it's valid for any I. That's right?
Yeah.
But this holds only correct when? What if I have here a store, but after the store I have 8 and 7. 4 minus 7 is minus 3, so I cannot collect them. It's only valid if K is bigger than
K is
C.
bigger than 6, so K minus C.
But if C is bigger than K, I cannot avoid sadness, and I cannot go to any state because there is no state for minus 3 here. You got it? So having a slope will not always guarantee that I can collect, because maybe the credit in this busway is bigger than my back capacity.
Yeah.
You got it?
Yeah.
Is there any problem?
I have a question.
Yeah, tell me.
So how do we get from the complexity?
Yeah, exactly. Let's move on. How did we get this complexity? Okay, the number of vertices in this was how many?
For each path, or what?
In the original problem, we had n clearings, so it's exactly n, and the edge is at most he told you, he stated that each clearing has at most 5 tries, means the edge is at most 5n. Okay, this is before making the work around. We have made another vertices. Okay, for each clearing, how many vertices do we add? For each vertex, we added many states. Our state was, no, not 5, we are considering the general case. When we have case fields, how many states we can add? From 0 to k, which is k plus 1. If we have 4, we added 5. We had 4 fields, we added, if the case was 4, we added 5 states. If we had k, we add k plus 1. So now we will have, the vertices will be equal to n multiplied by k plus 1. Right? What about the number of edges? The number of edges was originally how much? 5m. Okay. Will the edges remain the same or it will differ? Focus with me. Here we had how many edges? 1, 2, 3, 4, 5, 6. But here 1, 2, 3, 4, 5, 6, 7, 8. Or 7. Why? This graph is very small, so you will not imagine how much the edges can grow. But here, from B to T, I had only one edge. But here from B to T, I had 2 edges. Why? Because I am considering each state. Here I don't consider states. Here, how many states will give me not sad? Will be not sad? 2. One will be sad. So those 2 will have 2 different states at the target. But here, I cannot solve it because they only have one state. So considering this workaround, I can have many edges, unlike the original problem. That's right. So how many edges I can have at maximum? How many edges? Originally there was 5 edges, right? After making this workaround, I also can have 5 n k, smaller than this one. Okay, or 5n 5k plus 1. Because if I have connection to every state, it will be k plus 1 connection at each clearing, but it will not reach this, so I made smaller than or equal. Also because he told you that at most 5 tries. So now the vertex is bounded by nk, the edge is bounded by nk. So the order will be nk log nk, which is required in the original problem. Did you get it? Is it hard? Yeah, nk because the number of vertices originally was n, but now it's nk. And the number of edges was originally smaller than 5n, now it's smaller than 5nk. So it's now bounded by nk log nk because the original complexity is d log v. When we plug in this complexity, which is nk instead of v, and when we plug in 5nk instead of e, to be nk log nk because all of the others are 5 is constant and the 1 is constant.
Makes sense.
You got it? You have any question? Did you understand those 2 problems? This is one and the previous one?
Previous one.
This is harder, much harder.
This one is easier.
No, it's harder. It's hard to think about it. When I illustrate it, it's easy.
Yeah.
But thinking about creating new vertices is somehow hard. But the previous one is binary search, but before binary search, I need to get the distance from for the nearest center. So multiple Dijkstra will give me n squared of n. So it's not valid. So I need to make one Dijkstra which requires a single something. This is the idea for the previous one. This idea here that I cannot make Dijkstra because my main objective is not the shortest path. Shortest path when being happy or when avoiding being sad. So I need to eliminate some paths. So in order to make this, I cannot eliminate from the original graph because I will remove this edge and this edge may be considered in different pathways. So removing it will not guarantee the solution for me. It may like make the older graph incorrect. But here I am only visiting the valid states. So I'm sure that any valid state will go to a negative state that doesn't exist. So only the states that reach the target will be considering or making sure that ensuring that the girl will not be sad. And then I will take the minimum out of all of them. You got it?
Yeah.
Very good. I have recorded it and I will upload it for you.